A series of lectures by Professor George Phillies, based on his text, Elementary Lectures in Statistical Mechanics. And stand by for our future works, Introductory Mechanics, Harmonic Oscillators, Polymer Solution Dynamics, and Game Design. The course associated with this lecture has been used successfully with physics graduate students, chemistry graduate students, and physics undergraduate students. Whatever your background, you should realize that you will have to adjust your speed to what you can handle and how fast you can handle it. I do give one bit of advice to every student. Some people learn by doing lots of problems. Other people find the problem something they have to get out of the way before they can sit down and think about the material and come to understand what the material actually means. Whatever your best approach to studying, please use it and use it well. The organization of this course and this text is rather straightforward. We have 5 parts, namely classical separable systems, quantum separable systems, inseparable systems, dynamics, and advanced topics. What do we mean by a separable system? A separable system is a system in which, even though there are a lot of atoms present, we can calculate carefully the behavior of 1 or 2 atoms, and having done that, the rest of the system falls into place with a minimum amount of work. Some of those systems follow the laws of classical mechanics, like the ideal gas. Others of those systems follow the laws of quantum mechanics, as is seen in calculating the specific heat of a diatomic molecule. Beyond the separable systems are the inseparable systems. The inseparable systems are systems in which you have large numbers of interacting particles, like a liquid, and you actually have to worry about what all of the particles are doing at the same time, rather than finding some clever choice of coordinates that makes the system look as though it only contains 1 particle, or perhaps 2 particles. After doing those topics, we will push on and discuss dynamics. We'll discuss correlation functions, we'll discuss the Mori-Swansig theorem, we'll discuss linear response, we'll discuss various ways of asking what a system does as it advances in time. At the end of the course, we'll take up a few advanced topics having to do with light scattering spectroscopy, with the motion of Brownian particles in solution, and with the motion of polymers in solution. There are a few ways in which this book differs from the many other excellent statistical mechanics books that you can find in your library. First of all, I've tried to show how you can learn and understand the material, as opposed to trying to prove how much I know about statistical mechanics and how obscurely I can say it. Second, I am extremely fond of dotting all the I's and crossing all of the T's. When you get to aside C in my book, you'll see a discussion of the Gibbs paradox. There are 2 important features of the Gibbs paradox which are not always said correctly in all those other books. First, the paradox was not due to Gibbs. Second, Gibbs did not believe there was a paradox because in Gibbs' formulation of statistical mechanics, the paradox does not exist and everything works properly from beginning to end, even though Gibbs used classical mechanics for his analysis. And that brings me to the second point in which this course is not quite the same as other courses, namely quantum mechanics is left in its proper subsidiary location. There are a few extremely interesting quantum systems in which statistical mechanics can be analyzed and plays an important role, and interference plays an important role. There is an important question of why quantum statistical mechanics and classical statistical mechanics agree with each other in all of the places you would expect them to, but the number of systems in which quantum effects such as interference play a major role is really very limited. Analysis of those systems turns out to be extremely difficult. Finally, there were two great 19th century scientists who analyzed and developed statistical mechanics: Josiah Willard Gibbs, who was at Yale University, and Ludwig Boltzmann, who was in Austria. This text follows quite specifically the Gibbs formulation of statistical mechanics and not the somewhat different Boltzmann formulation. You'll see what that means as the text goes on. With those remarks, we conclude my introduction to statistical mechanics. We'll start in the next lecture by discussing what statistical mechanics is like and in what ways it resembles other sorts of scientific theory, classical mechanics, electromagnetism, or quantum mechanics.